it should be more difficult. So you have electric field, and then we try to calculate the electric field for different cases with a charged particle, dipole, line of charge, charge of this, and a point charge in the electric field. So we will try to derive some equation for different geometries. And of course, we'll use the calculus. So it will be very interesting rather than just memorizing some formulas. And at the end of this chapter, I will also introduce the dipole, what is called the electric dipole. Electric dipole. So actually, in the previous chapter, we know that if we have two charged particles, no matter it's positive charge or negative charge, they will have some electrostatic force. And how we can calculate this force is to use the Coulomb's law. You just substitute the charge amount of two charges and the distance between them, then you can get the electrostatic force, attracting them or repelling them. So it is nothing special. And if you have more than two charges, then you can calculate the force one by one, and then you add them together by a vector sum. So here we try to simplify it a bit because we have two charges here. And actually here is trying to say that we have two charges, and actually you know that both are, if they are both positive charge, then you should know that they're repelling each other. They're repelling each other. Actually, they are not touching each other, but they can repelling each other. So it's something strange. It's something strange, right? Because if I try to push you, then you should know. Then you should know I'm pushing you. Then you fly away. Then but this one they do not touch it. They have a distance, but actually Q1 push Q2 away and Q2 push Q1 away in the opposite direction. So how do Q1 know Q2 exists? How do Q2 know Q1 exists? So the physician tried to introduce a concept called the electric field, which means that just say for particle 2, it is a positive charge, so it sets up an electric field at all points in the surrounding space, even if the space is vacuum, 真空的. If we place Q1 in the space, then it can feel the field generated by Q2. So it knows the existence of particle 2. And actually, the field generated by Q2 pulls Q1 away. So this field is called the electric field. So the physician tried to explain this phenomenon this way. So now they try to define the electric field in a mathematical way. So in the previous chapter, we know that the force between two charged particles can be calculated by Coulomb's law, but now we should know that the electric field generated by a positive charge shouldn't be related to another charge. Shouldn't be related to another charge. Actually, I want to know that if my charge is Q0 and then I place here, I should be able to know that there are some variable that doesn't change. If my Q0 become 2Q0, then the force may vary with this one. But actually, there should be the electric field which doesn't really change according to my charge. So this is called a test charge. So now suppose we place a positive test charge here, which has a charge amount Q0, then the electric field is defined by the electrostatic force F divided by this Q0. And you know that, for the Coulomb's law, suppose this one is capital Q, and the distance between them is small d. So that you should know that the force is somehow like K times Q times Q0 over d squared. So if we just substitute this F into here, then we know that E equals K Q0 over Q0, so that they will cancel each other. So E should be somehow like this, which does not depend on Q0 itself. So this is good because the field generated by the upper charge shouldn't be related to how large the test charge is. So this is a very good definition. Very good definition. And the SI unit for E should be newtons per coulomb. Or in chapter 24, you know that it can also be volts per meter. Both are okay. It depends. You can choose either of them during the quiz or exam, but actually you need to write it correctly. Up till now, any questions? Okay, it's just a definition. So here introduce another concept called the electric field lines. So electric field lines is somehow abstract, but actually try to visualize the direction and the magnitude of the electric field, which means that it satisfies two conditions. The first one is the electric field vector at any point is tangent to the field line through that point. In Chinese, it's called 这个 electric field lines 就是那个电长线的切线，就是那一点的电场方向。So the electric field vector, so the electric field vector at any point is tangent to the field line through that point. And the second condition is that the density of the field line in that region is proportional to the magnitude of the electric field line. So you can see it here. For this part, you can see the lines are denser, 比较密的 dense, dense. 就是密度比较高。Then the magnitude of the E field at this region is higher than this region. So visually, you can see that the line here is less dense, and the lines here are more dense. So it's just visually you can be able to know that. And for this one is an infinite charge plate. Then it's chapter 24 or this chapter. You should be able to know that the electric field is actually uniform. It's actually uniform, or they will all point to the same direction. So you can see that all the lines are parallel to each other, so that no matter which region they are as dense as the other region. And the other point is that for this one is a negative charge, so that the electric field will point to the negative charge. And here it is a positive charge, so that the electric field line will point outward. For the right side, you point to right. For the left side, you point to the left. If it is a positive charge, the electric field line will be somehow like this, point to the outward. If it is a negative parallel plate, the electric field line will be somehow like this. So this is to visually express the relatively how large the electric field is. The force on the positive charge near very large and non-conducting sheet with uniform positive charge on one side. So now here's another example. We have two positive charge. One is here, one is there. So that you should know that they should have a electrostatic force repelling them. If you draw the electric field lines, it will somehow like this. Actually, for every point, you can be able to calculate the E field. For example, if you want to calculate the electric field at this point, you can imagine you have a test charge Q0 here. Then for this charge Q0, it will have a force, electrostatic force from the upper charge, and then you have another electrostatic force from the lower charge, and then you add them together, F1 and F2. Then you have a net force, and then you try to divide it by Q0. Then this is the electric field at this point. So actually, if you really want to plot this out, you need to calculate the electric field at every point, so that you can get this graph. Actually, I will not ask you to do so, but it's just to demonstrate, visually demonstrate how the E field looks like. So actually, it tells you that the pattern itself suggests that the particle repels each other. So I'm not sure how to convincingly tells you the reason, but actually you can just see the line here. They are somehow like this. Which means that if you place a positive charge here, you will try to follow the electric field. And actually, both of them are positive charge, so that they should follow the electric field lines somehow like this. Actually, they should be this would be somehow, this one should go up, this one should go down. But if you just imagine you place another positive charge maybe here, then it should follow the electric field line. So actually, I just explained you can use the Coulomb's law and then you substitute in the original definition. Then you should be able to know that if you have a charge Q, um, then the electric field generated by this charge is like this: 1 over 4 pi epsilon 0 times Q over R squared and times the unit vector of R. So similarly to last chapter, if you have a charge here, so the R axis should be original from this charge, and then maybe for this point, the R axis is like this. If you for this point, the R axis should be in this direction. So this is called the polar coordinate, 极坐标. So actually, the R axis can rotate. It is different from the Cartesian coordinate. Cartesian coordinate always have the x-axis on the horizontal direction and the y-axis on the vertical direction. But for polar coordinate, the r-axis depends on what is the point and your original point. And for this case, the original point always placed at the charge, so that if you consider the E field at this point, so the r-axis point to this side, and the R hat is here. Of course, the R hat have a magnitude equals to 1. And for this point, you have R hat here, and for this point, you have R axis, and then R hat is somehow like this. So this is the most, actually the simplest case, which is a single charge. Single charge is very easy. It should be somehow like this, and then it says if there are more than one charge particle set up an electric field at a point, then the net electric field is the sum of is the vector sum of the individual electric field. The electric field obeys the superposition principle. It's just like what we have done in the previous chapter. If you want to calculate the if you want to calculate the electrostatic force for a charged particle from more than one charges, you calculate it one by one and then add them together. Here is the same. If you have more than one charges, then it will generate. Maybe you have a maybe plus Q here, then if and you have another plus 2Q here, maybe. So if you want to calculate the E field at this point, so you can calculate the E field generated by plus Q. So it is E1, and then you can calculate the E field generated by this plus 2Q, and then you have E2, and then you add them together. So similar to the Coulomb's law, if Q is positive, you know that the E field should pointing outwards. If Q is negative, then you know that the E field should point to the charge. So here is a I think I can still load it in the last. Yes, okay.
This simulation deals with the electric field
Yes.
near a point
So
charge.
here we have
First,
a charge,
investigate the electric field from a
and
single
maybe you can
charge,
see my
noting what
cursor.
happens as you adjust
So
the
if this
sign
is a
and
positive
magnitude of the charge.
then you can
Then
see
add a
the
second charge, adjusting its
direction of
sign
the
and
E field.
magnitude to see how that
the
affects
arrow.
the net
the arrow.
electric field.
And if we have another charge, then okay, you can feel the electric field line. If both of them are positive charge, they should be somehow like this. If one of them are positive and the other is negative, you can see that the electric field line is somehow like this, somehow like this. Actually, the charge, this is plus Q, this is negative Q, it should be somehow like this, somehow like this. Somehow like this. So if one is much larger, one is 4 millicoulomb, and another one is which means that one is 4 unit of charge, and the other one is 1 unit of charge. Then you can see that this one is suppressing to this side, because the left one is stronger, and it show more arrow. We have more arrows here, and this one is weaker. It shows only 3 arrows. But this is just a demonstration. You cannot say, oh, why it only draw 3 arrow, why this draw 12 arrow. It's just a demonstration. Comparatively, it's just this is 4 times bigger than that. So this is a visually demonstration for the E view. Okay, so